Hello, going to go over the partner test FRQs here. Just give you a little bit of a train of thought in terms of why the problems are set up the way they are, and then look at how we set them up. So first of all, as we look at this first question, a couple things that stand out naturally are going to be that there's a 10% probability here that they'll be upgraded. The outcome is independent. That is going to be a very big factor here as we look at what type of question we're dealing with here. And then we look at what is a success and a fail in this situation. And so the idea is that getting an upgrade would be a success. So we look at success as being an upgrade. And then a fail, of course, would be not getting the upgrade for seat on this flight. So what is the probability that Sam's first upgrade will occur after the third flight? Well, when you look at this, this is really saying or asking what's the probability that it would be greater than or equal to 4, or you could say what's the probability that it's going to be greater than 3, because these are discrete, because there's not a continuous, there's not a mu and a sigma. This isn't a z, this isn't a normal curve situation. This is discrete values, meaning first flight, second flight, third flight. There is no 1.325 sort of a scenario here. Now, the problem is that if it occurs after the third flight, then after the third flight would mean that it could occur on the 50th flight or the 80th flight, and you don't want to go through that process. And so when we get something like after, or it could have been at least 4 flights or something like that, the easiest way to answer that is going to be to just go ahead and turn that around and make it a 1 minus the chances of it being 3 or less. Okay, so the options here naturally would be the first flight, the second flight, or the third flight. So what we're really looking at is, in general, what's the probability that the upgrade happens on the first flight? Well, it said there's a 10% probability of an upgrade, so that would just be 0.1. Okay, so the chances of the first upgrade happening on the second flight would mean that he first has a fail on the first flight and then succeeds with an upgrade on the second flight. And then finally, to have the first upgrade be on the third flight would mean that there's 2 fails. Okay, so 0.9 times 0.9, or 0.9 squared, and then times the probability of a success. Okay, so what this is doing is this is now looking at 1 minus the chance that it's the first flight, the second flight, or the third flight. And when you subtract all of that, it ends up giving you about a 0.729 as an answer. So you can see that that we'd be subtracting 0.271 here from those first three flights, which means there's now a 0.279 chance that we'd have our first success after our third flight. Again, with this being a geometric, you could just do the 0.9, excuse me, the shortcut there would be to just take 0.9 to the 3 as well, which you could do as well for any scenario where it's more than a certain number of trials for a geometric. So if it would have said first upgrade after the 10th flight, you could just do 0.9 to the 10, and that would also give you the answer. But this is a pretty clear way of looking at it here, and this is certainly a way that it seems more repeatable just in terms of you can see how that's set up. Part B here, things to look at here. So we're saying upgraded exactly 2 times. That would mean exactly 2 successes, and we have this fixed number of trials now. So that fixed number of trials being the 20 flights, now it's not saying how many until we get an upgrade. It's really saying out of the next 20, what are the chances we get exactly 2 upgrades? So this has the characteristics of a binomial with the fixed n right here. Okay, that's usually the first thing that stands out with a binomial. They said they were independent. The probability of a success was 0.1. That doesn't change. And there's a success and a fail, which would be upgraded or not upgraded. So this question here would be asking for a binomial. Again, the binomial formula is on your formula sheet, but we'd be looking at capital X equaling 2 here. We have 20 flights. Choose 2 successes. Again, there's no fraction bar there. This is simply 20 choose 2 is how many different ways we could order 2 successes and 18 fails. Then we have the chance of a success to the number of successes, and the chance of a fail to the number of fails. Now, on your calculator, that would look like this. So that's second vars, binomial PDF, 20 trials, a 0.1 chance of success, and 2 successes. Now keep in mind, on the AP exam, you can only write this if you define what 20.1 and 2 stand for. So you could write binomial PDF, trials equals 20, probability of a success equals 0.1, number of successes equals 2. So you could write that, but again, the formula may just be easier. In this case, the final answer ends up being 0.2852. The third one, so give that a little square as well, a rectangle. Next one, Sam will take 104 flights next year. Would you be surprised if Sam receives more than 20 upgrades? Again, much like part B, we've got more than 20 is a number of successes. We've got 104 here is the number of trials. Okay, so this has the binomial makings again. In this situation, the difference is, in this case, that we are now looking at the probability that X is more than 20. Now, again, when you get a situation where it's greater than, you're probably going to find that the easiest way is to change this around to be 1 minus the chance that it's less than or equal to 20. Again, if this were greater than or equal to 20, then you'd be subtracting 19 or less. But because this is actually greater than 20, you have to subtract the 20 or less in this situation. Now, what would this look like? Well, in terms of a binomial, this would really be 1 minus, and then you would have, I'll change colors here, you would have 104, choose 0, chance of a success to the 0, chance of a fail to the 104, plus dot 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 plus, all the way up to 104, choose 20, chance of a success to the 20, chance of a fail to the 84, because again, these two have to add up to 104. So this is really what this looks like. Now, our calculation of this, again, is going to be made much quicker by working on the calculator. And the calculator has that function binomial CDF. And again, CDF is going to start at 0 and go up to the number we have it go up to. So here there's 104 trials still. There's a 0.1 chance of success. And we want this to go up to 20. Again, if we did not do the 1 minus here, we would have to PDF 21, 22, 23, 24, all the way up to 104. But by doing a 1 minus, we can utilize that CDF function on our calculator, which takes us back down to 0. So we go, in this case, 1 minus that binomial CDF, which ends up being, sorry, I'm working back upward here now, 1 minus 0.9986, which is 0.0014, really approximately 0.0014. So 0.14%, which means that's about 14 out of 10,000 times we'd get more than 20 upgrades. So the question is, would you be surprised if Sam receives more than 20 upgrades? Absolutely, we'd be surprised, because that probability is so low that he'd receive more than 20 upgrades. Again, we can kind of use 0.05 as that threshold. Now we're below 1% even chance that he'd get that. So we'd expect it less than 100, 1 in 100 times. And so for him to get more than 20 upgrades, so this would be extremely rare. So yes, we would be surprised in this case. All right, on to number 22. 22 is a true random variable problem. Okay, so this is a probability distribution. Okay, again, there's formulas on your formula sheet for this in terms of calculating the mean, and the mean is going to, in this case, mu of c is going to be the summation of the x sub i's times the p sub i's. Okay, which in this case, and again, you do have to show your work, to calculate the mean here, and again, this is how many children's tickets a customer would buy, 0, 1, 2, or 3. 40% of the time they buy 0 children's tickets, 30% of the time they buy 1, and so on. To calculate the mean, then, you have to take the value on the top, the 0, and multiply by its probability, plus the 1 times its probability, plus the 2 times its probability. Again, you do need to show this work. Not that it takes that long, but you can see it's a little bit of busy work, but that ends up being an answer of 1. So that means an average customer is going to buy 1 children's ticket to go along with whatever adult tickets they buy. So that is 1 exactly. Now the standard deviation is also on your formula sheet. It looks like this. It's the summation of the x sub i's minus the mu times the p sub I, which means, in this case, it's all based off of the mean value and then how far we are from the mean with our answer and then how likely that is to occur. So what I mean by that is if we look at the first one being 0 minus the mean squared times the probability of a 0. So since 0 is the highest probability, this one's going to have the most effect on our standard deviation because it's 40% of our observations. Keep in mind, we're going to get the exact same thing as if we were to write out, in this case, since these are all to the 10th, this is the equivalent of having 4 zeros, 3 ones, 2 twos, and a 3. Okay, these values would be the exact same as this table. So you could put these into a list and get the mean and standard deviation that way using one variable stats and just look at the X bar and the S, and it would give you, or I guess in this case, the sigma, and it would give you those same values that we're going to get, because that's all this table is doing, is just summarizing a collection of values. Okay, so the 0 has the highest probability, so that will have the most profound effect on our standard deviation. Put the radical in there. Now, of course, the 1's going to have no added value to our standard deviation because it is the same as the mean, but it does take up 30% there, so that's going to help keep our standard deviation down. Then we have 2 minus 1 squared, and that probability is 0.2. And finally, we have 3 minus 1 squared, and that probability is 0.1. What it ends up equaling is the square root of 1, which is just 1. Even though the square root and the non-square root value here are the same, you do need to include the square root. When this was on the AP exam, if students solved and still got 1 but didn't put a radical there, they got partial credit only instead of getting full credit, since they technically found the variance, even though the variance and the standard deviation are equal here. So that's part A. Part B now brings in adult tickets. Okay, so this is now rule 2 for means and variances. So what we're really looking at here is mu of children plus adult and standard deviation of children plus adult. Okay, so this is not scale factors here. This isn't, we aren't bringing in cost yet for each of these tickets. We're just bringing in the children and the adult. So the mu of C plus A is just by rule equal to the mu of C plus the mu of A. And the mu of C for the children was 1. The mu for the adults, it says here, is 2. So that just means that people are buying 3 tickets on average. For the standard deviation, again, when you add 2 groups, you have to add square root, just like you would with the Pythagorean theorem. So in this case, we square the children's standard deviation, which was 1. So this is 1 squared plus, and we always add here, and then the standard deviation for the adults is 1.2, so that's 1.2 squared. So we add those up, and then we take the square root. This equals the square root of 2.44, which is approximately 1.562 tickets. So that means a customer is on average buying 3 tickets, give or take about 1.562 tickets either way. Again, we use this is the rule 2 for means and variances here. Now part C brings in cost, and so this becomes the scale factor. So this becomes the B in our rules for means and variances. So for instance, so what we have here for mean is we have the child tickets are now 15C, because that's the scale factor for the child tickets, and the adult tickets are 25, so that would be 25A. So for the mean, it would be 15 times the mean number of children's tickets, which was 1, and 25 times the mean number of adult tickets, which was 2. So that means on average, the average ticket purchase is $65. Now the standard deviation, again, it's with the cost, the scale factor in play here. So what we would do here is, this is now rule 1 and rule 2. So we've got the big radical, and now it's scale factor squared times standard deviation squared. And again, standard deviation for the children up here was 1. So that would be times 1 squared plus scale factor squared, that's B squared again, times sigma squared, which is standard deviation for the adult, which was 1.2 squared. And that ends up being, when you dust settles there, when you calculate all those, it's root 1125, which is approximately a standard deviation of $33.54. So if there were a part D, they might ask something like, what's the probability that a customer spends over $100? Okay, so over $100 here would then be asking a scenario of what's the probability that X is greater than 100? And then we'd have a Z, which would be 100 minus 65 over 33.54. We'd calculate the Z and we'd normal CDF from that to 99, and that would give us the probability that somebody spends over 100, presuming this is normally distributed in terms of ticket purchases. The last thing I want to note here really quickly is, had this question not made the statement about being independent, which it does right here, let's put this right here in part B, had it not made the comment about being independent, we would not have been able to calculate that standard deviation, and we would have been out of luck, and we would have needed more information, because that would have meant that children's tickets did play a role in how many adult tickets were purchased or vice versa. So the independence was key there, and that's where we get these final calculations. Thank you for listening. As always, please ask if you have any questions.